Good afternoon. Welcome to my talk. Thank you for dropping by. So my name is Jibin Zhan. I'm lead the platform and product engineering in Conviva. So a little bit about Conviva. Conviva is a video experience management platform that maximizes viewers' engagement. So first, the online video, which I think everyone now knows that is a hugely important application. Besides the YouTube and Netflix, who are the early pioneers, and also success, many content owners, like media companies and infrastructure companies, are also moving from the traditional delivery of video to internet streaming. So some major industry shift actually in the last couple of years happened. For example, before you can only watch HBO through the subscription of cables or satellites. But since last year, HBO actually starting offer the HBO Now service directly through the internet. Similar things happened to ESPN through the Sling TV, so you can cut the cord while still watching ESPN. Verizon Go 90 did a similar thing, but it's on the mobile platform. And of course, Facebook, Twitter, all start working a lot on their, invest a lot on their video application. Most recently, Amazon Prime, the Prime Video now become a standalone, can be a standalone service directly competing with Netflix. So it's a hugely important thing happening in the last couple of years. We say it's almost like a big bang moment of this online video industry. Just a little bit more about this. Right now, more than 75 to 78% of bytes on the internet is actually video traffic. And it's growing so much faster than any other traffic. Very soon, the internet will become almost like a video networking. So making this working well is extremely important. So internet video actually streaming is actually very hard because traditional video delivery is all on the dedicated infrastructure, cables or the satellites. But internet video, you actually have many entities involved, from the publishers on the left-hand side. They push the content through the CDNs and through the backbones and then through the ISPs, and then come to your device at home or on your mobile. No one really, many things involved here, no one really have the end-to-end control or even monitoring. So, so it's actually very hard to make it working well. But on the other hand, the quality of the experience is extremely critical to the end user. So here just a very simple reports from us showing that how the quality impacting the user's engagement. And you can see just a little bit of quality degradation. The engagement is reduced quite a bit, and over time it's getting worse. Similarly, on the right-hand side for the churn, so basically if your quality is not good or experience is not good, they're going to churn out. So essentially, the viewers expecting the TV-like quality, or even better, because they're expecting this new technology and all this stuff, right? So you should have a higher resolution, probably, and maybe a higher frame rate. Actually, like YouTube already offering higher frame rate than the default, like a 30 is usually. And a lot of stuff like 3Ds and the interactivity, many things beyond. So it's actually, the user expectation is much higher now. So from the publisher or service provider point of view, they really need to know the end user experience to keep the business working. There's a lot of things, basically any of their success depends on that, and their competitions depends on that, and of course the business. So now, Conviva is the company we actually provide we call it experience management platform. We are trying to actually bridge that gap, and so we actually first focus on the end user experience monitoring and measurement and monitoring. So on the right-hand side, we collect a lot of detailed information from every end user's device and monitoring and getting about the end user's quality experience and data. And of course, we also work with the publishers, which are so we get a lot of information about the content, about how they do the content publishing. And increasingly, we are also working with the CDNs and ISPs. And they become our partners, and they're getting their data about their internal structures and their server IPs and their network topologies to us. So we can actually really utilize all this information together to provide a better end-to-end user experience. Now, all this is based on huge amount of data, and the data also granular. We collect a lot of granular data, index also about a lot of rich metadata. Here, just a very quick show about from the user, from the device end user point of view, the data model. It's, for example, a lot of things happening on the user side can be modeled as state machine. So, for example, the screen size, like a full screen or smaller or default, and player state, you're playing, you're buffering, rebuffering, your pause, you stop, all these are, etc., are all modeled as states. And then we collect all the events about the state change from the beginning that the user start clicking the play to when they actually see the first frames, when they change the full screen, and when they change the probably different CDNs or different bit rates. All this stuff we collected and sent to our backend. So we actually deployed a system over the years and supported a lot of customers. This is just a list of sample customers, hundreds of customers. A lot of them are premium customers across different industry sectors, from advertisement-based customer, we call it AVOD, or subscription-based, and also infrastructure like the Comcast and Level 3 and Dish and DirecTV. So a little bit more about the data we collect. We have billions of streams collected across all the customers over per month, and touching billions of devices and cover most of the countries and most of the CDNs, most of the ISPs, and we have more than 500 client libraries actually integrate across all the customers. So a lot of kind of sensors actually over the internet. Now, just a little bit about this. So we support all these customers. How we actually do that, right? There are many use cases. We essentially classify them into 3 kinds of use cases and supported by 3 kind of stacks. The first one we call real-time. So you need real-time monitoring and real-time alerts and real-time optimization for the video quality. Real-time alerts, for if they have problems, you want to know the problems as soon as possible, get alerts. So this one we implement through we call a live stack or real-time stack. In the Lambda architecture, this is called speed layer. So it's and then the another stack we call a historic one. This is provide kind of near real time. So the real time one is in the seconds, in a few seconds delay, and usually it's every second we update, so you can get alerts as soon as possible. The near real time is delays in the few minutes. So here is like I know that when so the and then this is if you based on the Lambda architecture, it's the batch model layer portion. So provide near real-time metrics, but they also provide the entire history. So you can look at the previous time windows. You can see, over the years, and we can do benchmarking also. And then last one we call it offline, which usually people don't talk as separate stack, but really if you actually in the last couple of days, you actually heard a lot of people actually also talking without explicitly mentioning that. It's kind of, but in the Lambda architecture, kind of part of batch, but they are actually very different characteristics. The live and historic ones, the 2 stacks, is mostly doing the predefined calculations and predefined rollups. The offline ones is really providing additional capabilities to do in-depth and ad hoc analysis, data exploration, machine learning, model training, those activities. So it's quite different from actually near real-time, the other batch model. So the implementation of all these three stacks is based on the old architecture we have over the years. You can see the real-time stack is built based on the proprietary implementation. It's pretty complex implementation. I will talk a little bit more. And then the near real-time, I think most people is kind of, as most people do, is using Hadoop, MapReduce-based implementation. And the offline stack is a collection of actually quite a bit of different tools from Hadoop, basic Hadoop, Hive, and we also start using Spark when Spark actually coming out. We are actually one of the early Spark adopters, and then R, and then we also have custom-built neural networks. So that's, you can see there's three quite different stacks implementation. Now, what are the issues? I think as most people know that in Lambda architecture, one of the big issues is you have to support different stacks with different code. And the same thing here is code discrepancy among all three separate stacks. The real-time ones is based on the pure update model. So it's, and then the near real-time is based on the batch. So they are quite different model. The offline ones, we use a collection, I mentioned a lot of different collections, majority of them is Hive. So you have a lot of calculations, logic scattered in the Hive queries. And we try to reduce these kind of things to use some standard UDF and UDFs to try to, kind of help to a certain extent, but fundamentally they're different code. And now I want to touch a little bit more about the real-time stack. It's fairly complex. It's all based on the mutable objects, the updated state inside memory. And then you have multi-threading, locking. And also to scale it out, we have to come up with how to partition the data all proprietarily. We come up with very specific ones. It's kind of dedicated and to make the data partition load balance. If the data come in, it's not completely follow some of these assumptions about the traffic will causing some issues also. And then, of course, because the code are different, the things you calculate out will be different also. So we call it the metric discrepancy across all the three stacks. Now with three different stacks, you also occur a lot of overhead from development point of view and the deployment point of view. A little bit more about the real-time stack. So you can see, so here just an example of a particular video playback session. And the message come in, we call it heartbeat from the client. So whenever we receive a heartbeat, we immediately update the state related to represent the current state of the playback. And the next message come in, we update again for this particular session, and so on. So you need to do that for also millions of sessions at the same time, and all sync asynchronously. And then you need to derive some of the metrics to aggregate them, and that's where the multi-threading and locking happen. The batch-based, Hadoop-based, I think, is basically you batch multiple messages within the batch. Usually, for example, 5 minutes as a batch size. So many messages coming in, so you can reorder, you can make sure they're ordered properly, and then you process them in one shot. And then you update the state at that batch boundary. And usually, you write the result out, the state out to a persistent store, and then you go on like this. So it's a different, quite different model. Now, we see all these issues, and we actually thinking this is not maintainable. It's very hard. And that's where we start thinking about how to really change that and how to come up with one unified framework to do that. Just a little bit story about the Spark streaming. Here, of course, we moved the real-time stack to Spark. Spark streaming started as an intern project in Conviva. When TD is an intern working with us, we say this is a problem we need to solve, and then that's where the Spark streaming really started. So that's about 3 years ago. So that's our vision at that time. So we moved the Spark. We want to move the Spark the real-time to something similar to the batch because it's so much more easier to reason and to manage and hopefully share the code. So based on this vision, we have the new architecture is everything moved to convergent to Spark, including the offline ones. And then we try to maximize the sharing across all the code. Hopefully, vast majority of the code will be the same, just some kind of configuration you make because of the requirement of different stacks. And then the offlines, of course, we also use Spark and try to consolidate that. We have a little bit of luxury here. Where all our data science scientists in our team are also software engineers also when we build the team in that way. So they all can pick up the new Spark environment to do that. And of course, the Databricks environment really helped us to bootstrap to make this transition much easier. I'll talk a little bit more about this later on. And then the unified stack is all based on kind of a batch model. The semantics is much easier to reason. The key thing here is you need to be able to write the code in a way that you can handle different batch size. So, for example, the batch size need to be can be varied, and whether each stage when you update the state or change the state is whether you need to persistent to the persistent store, you need to be also handled differently. So those are the key things when we build the unified stack. A little bit about the code fragment is fairly straightforward. Here is you get this stream from the raw logs, which is all the message we call. And then you do a transform just like a map, and then you do update state by key. And that's essentially your reduce function to update the key, the states. And then for certain a number of batches, you decide to save to the persistent store. That's high level. A little bit about this update state by key and the performance of when we start actually working on this, the performance is a big issue because we actually, as I mentioned, the real-time stack is in the seconds. So the delay and all the stuff, the batch size is a couple of seconds. So the update state by key, the implementation is actually proportional of all the state in the system, not based on the size of the batch. So that's one thing we actually really thinking need to be really improved, and in Spark 1.6, that's they change that to map with the state, which only touch the state you really need to update. So that's important. This one, the real-time portion of the unified stack, we kind of finished all the ones and then actually deployed in production for over 5 months. It's still a lot of issues, like performance tuning and balance between the reliability and the performance, like how to handle the checkpoints. And our requirement of the real time is not like I don't need the accurate numbers. So we can tolerate certain of the things of the issues. So those are the things we need to continue to work on. So first, we want to make sure we can migrate to this stack first, backward compatible, and then we'll improve on top of that. A little bit more about the offline stack. The first thing is the offline stack, I think, is very important. I want to say for any company that is data-centric, I think the most important innovations are all happening through the data exploration and learning of the big data. So the speed and the efficiency of this offline data analysis and learning is the key to the success of the company. The other point, actually, I mentioned here, I won't be able to get too much into it, is that the data is not just, the offline analysis is not just for the data science team. You need to make sure it can be available, or a lot of things can be available to a lot of other organizations in the company. For example, customer support, sales engineer, and PMs. This is extremely important to make sure that they actually can leverage the power of the big data for the overall success. So it's a very important aspect to think about how to actually make the data offline data analysis available for other organizations. Now, so focus on the data scientist part. What are the important things for the data science team? The first thing is efficient access to all the data. I think a lot of people talking about the data lake, and all this really is about how to make sure the data management, data access is easy for the people who need it. And then data science usually want to work well independently. They can work without worrying about the shared cluster or shared resource contention. So they need to be able to do their work with all the resources needed. On the other hand, they also need to be able to work with other people, both within the team or across the organization. And then, of course, the interactivity for data exploration is extremely important. And the good and easy to use and powerful data visualizations are critical to data science also. Machine learning tools are very important to data science, of course. And then the other thing is the offline stack usually is not isolated. You have to be able to, you can't build everything from scratch, even though a lot of data scientists, they want to examine everything. But you really need to be able to reuse the existing production logic and production code, ideally, whenever possible. So that's a very important consideration when you build the offline stack. It cannot be completely isolated. Another thing is, I think a lot of people talk about is how to transfer the data scientist work to production. That's another very important aspect to think about. And I think data science team usually is not as thinking the way as engineer, but I think it's very important. They need to have certain engineering discipline also. For example, whatever the code they build, they have to have the right code management and the version management control, and potentially even testing all the stuff and integrate testing. And then make it easy for people to do design, the code review, and in the end also the result of the data review also. So those are the things I think we think are very important to the data science team. So we use them to evaluate what we do here. So just a little bit recap of the old architecture, right? It's a pretty messy one. So we get the data from the offline, the near-time ones to one or two couple of clusters. And then you run MapReduce Hadoop on top of that, and Hive. And later on, as I said, we add the Spark and then Databricks. And then the user interface and data visualization is mostly the tool we built on top of this big data environment mostly for other people to access the data, as I mentioned, like the other organizations. Even though the data science team also use them to improve their efficiency for some repetitive, constant, the more repetitive things. So the new architecture is much simpler, and it's all consolidated to the Spark on top of Spark and Databricks. And we're going to build the user interface and data visualization on top of that, so we can expose to other users who cannot directly use Spark or Databricks. So I want to touch a little bit about the Databricks. I think since we are probably the first customer also using Databricks, and so Databricks, the benefit for us is then we can utilize the cluster management. So instead of one shared cluster or a couple of shared clusters we used to have, and sometimes run into a lot of contentions, now everyone can launch their own cluster and manage the cluster, shut down the cluster when they don't need. The interactive environment through the notebook environment is really convenient. I think everyone mentioned that. And then the easy of sharing of the notebooks is also important. They have very good visualization like Matplotlib and ggplot inside R, which is also part of Databricks. And I think a reasonably good machine learning tools. I mean, they have MLlib and R and other packages also you can install. Another thing is the same code potentially can move to other stacks. And that's something we always try to achieve. That's one of the, and with Databricks, we actually can build a lot of features much faster. It's much harder to change the production environment. And quite a bit of features we actually built and tested and deployed on the offline stack first. For example, we recently we moved everything to Parquet from the other data format. And this is all in the Databricks environment, and we are going to move these to the production environment later on. So far, we gained a huge efficiency gain for the data science team. Pretty much everyone in the data science team right now, vast majority of their work is done within the Databricks for now. Even other engineers that are like the platform engineer also using the Databricks for their debugging of the production issues if they have, because they're the same shared data and some of the code. So this is huge efficiency gain for us. Here I just give a quick, very simple example about how we use Databricks for the machine learning problems. Here is we call long-term retention, and which is extremely important for a lot of customers. I think it's not just for video business. For most of business people of subscription-based business, people care about the retention of their subscriber. Usually, this kind of problem involve a lot more data. It's not just like a few short-term. Usually, it's long-term, like months or even years. For us, it's many billions of streams and millions of subscribers for each publisher and service provider. So we need to determine the right time intervals for this analysis and also figure out what's the drop-off of the subscriber. We need to find out the best features to build a predictive model. And one of the things related to build the features is handling of the categorical features with a lot of sparse value. A little bit about this, I think the categorical features, I mean, if you have only few dense values, like for example, what kind of devices, even though you have hundreds of them, are still pretty small and dense. I mean, one hot encoding would be good enough. But for some other features we have, like CTs globally and ASNs, which basically in the internet, ASN is a very important thing. It's about ISPs stuff. So it's tens of thousands or hundreds of thousands actually. The video content, the titles, millions of them. So those are how you actually characterize those build features about them is very important. And then you have to aggregate all these for all the subscribers. So what we did is something very similar to the text processing to do word embedding. So instead of try to use, we essentially figure out how the geolocation and ASN and time related stuff is affecting in the context of viewers watching all the sessions. So essentially we summarize all for each geolocation and ASN and the time of, for example, every day, we summarize all the characteristics from the video session. For example, the number of views for this particular geolocation and ASN and that day on that day. And the number of viewers, what kind of content, number of videos, and what kind of video types, and so this is user behavior side one to represent this embedding the features for this combination. Similarly, we put the quality rated stuff, for example, how long does it take for the users to see the first frames and whether they have a rebuffering, and those kind of all the quality related features also embedded in this. So basically, for the geo and the content, we use this kind of feature embedding. And you can see this is actually pretty tricky. It's not, you don't have a principal level kind of design to say, okay, why you have to include this feature or that feature, right? So that's why it's very important that you can actually have a lot of iterations about the feature. So here is the workflow. Usually, so what we did is we create a data frames with the features for each geo and day or the content of the combination. And then for each subscriber, we just replace their geo with the embedded feature of that geo or the content with that embedded feature. And then we aggregate all of them for each subscriber. And all this can be done within the Databricks environment, and a lot of iterative, and to decide what additional features. For example, we found out the user behavior, whether a particular user viewer watched after 7 p.m. versus during the day is very important. It's watched how much time they watch during the weekend versus work day is very important. So all these features need a lot of exploration and figure out, so a lot of iterations. So this is doing all this within Databricks really help us. And of course, we use MLlib. We tried a lot of different models. The gradient boost tree was the one we really liked it, and using the visualization within Databricks. Some sample example, you can see this is Databricks screenshot, and the standard ROC model for one of the example. It's very good result. So a lot more work need to be done. Of course, the real-time improvement is extremely important, and how to trade off the latency versus metric accuracy, and how to handling errors, the failures, important. And really want to get to much smaller, much faster reaction time, like less than 100 milliseconds real-time stuff, which we need in some of the applications, still need more work. And one last important thing is to make sure all the modular design, so we can reuse as much as possible across 3 stacks. A lot of other interesting, exciting works, like for example, anomaly-based detection, and working with the ISPs about the network insight to identify where are the problems. Very exciting projects we have here. Finally, we are hiring. So if you're interested in any of the problems I talked about, or any of the things we do, take a look at our career page and let me know. Thank you.
Awesome. We don't, unfortunately, have time for questions right now. So thank you, Jibin Zhan, for speaking today.